To prepare our solution using the dilution method, we first obtain 2 milliliters of stock solution with a pipette. Filling the pipette with stock solution to the mark on the pipette ensures that we have 2 milliliters of this solution. We add the 2 milliliters of more concentrated solution to the 500 milliliter volumetric flask, touching the side of the flask with the pipette. We add water to the mark on the flask. After mixing thoroughly, we have exactly 500 milliliters of a solution with a concentration of 1.60 times 10 to the minus 4 moles per liter.
If you're going to prepare a solution in the lab, there are 2 main ways that it's done. And the last example we looked at with oxalic acid was an example of this one, where you measure out a solid, so many grams, and you put it in so much volume of solvent to get a certain concentration. And that's what's done a lot of times. But there's a second way that's done a lot. And when you dilute a concentrated solution to give you one that's less concentrated. So let's go back to my silly sugar solution example. Let's say you make a sugar solution and it's like so sweet that kind of hurts even to like drink it down and stuff. So you thought, man, this is lame. So you decide to add some water to it. Well, the water, and you stir it around, the solution will no longer be as sweet. And of course, the more water you add, the less sweet it is, etc., etc. This process is called dilution. You're taking something concentrated and you're making it less concentrated. Now on the little picture right there, you can see that this kind of dark orange solution, that's a concentrated solution. You can tell there's a lot of like solute in there. On the other hand, the one to the right of it there, much less colored, much more dilute. The solute has been spread out because you have water. Now, where this is really handy for chemists is that most of the time, acids and bases, especially the strong acids and definitely the strong acids at least, they will be mailed to you, if you will, as a concentrated solution. And it's great sometimes having like 12 molar hydrochloric acid, which I think is the concentrated version. But man, you can't do much with it because it's so strong, right? It'll just cause all kinds of chaos. So chemists have to dilute the solution with water to make them more reasonable to work with. So this is actually something that happens quite a lot. And we'll look at an example of how you can take a concentrated solution and figure out like how much water you need to add to make it less concentrated to a more manageable solution. Here's an example of that. Let's say you look in the lab and you have 50 milliliters of a 3.0 molar sodium hydroxide solution. And that's fairly concentrated, all right? And for what you're doing, you don't want 3 moles per liter sodium hydroxide. You want 0.50 moles per liter sodium hydroxide. And the question is here, well, what do? So you need to take the 3.0 moles per liter down to 0.50 moles per liter. And you could, of course, take away solute, but that would be difficult because you'd have to evaporate water and figure it out. A better way, it would be to add water, because as you add the water, makes the denominator, the volume of solution, bigger, and that makes the concentration go down. It's like the sugar solution, all right? It was super sweet, you added some water, it was then more bearable. That's what we're doing here. You wouldn't want to drink sodium hydroxide, trust me, it's bad news for the body. Anyway, so what you want to do, add water. The water was going to be almost always the solvent, by the way, in Chem 221 through Chem 223. If you don't see it listed, it's just assume it's the solvent because it's like so important. But anyway, you want to dilute the solution. We're going to use dilution to figure out what's going on. But the question is, how much water do you add? All right. We know that the new solution will have more water than we started with. All right. It's going to have more volume. But how much? I mean, you could just wing it and start adding it, but that's not very scientific. We can do this mathematically, and it's actually not too hard. But we need to know, again, how much water to add to make the 3.0 molar solution turn into a 0.50 molar solution, or the concentrated solution will be turned into a dilute solution. In this problem, all right, the important part is that you're not adding any more sodium hydroxide. You're changing the volume, but you aren't changing the solute, the amount of solute that's present. So if the moles in the original solution equal the moles in the final solution, then we just have to realize that we can set them equal to each other. The little picture in the right, if you count up the yellow dots in the blue, all right, this one would be a concentrated solution because there's a lot of yellow dots and not that much blue. But on the right-hand side, you have the same number of yellow dots, but in a much wider area, all right, that's because you have more volume. So that would be a dilute solution. And we just want to figure out exactly how much to dilute the solution to. In this problem, we can do this by looking at the units. We had a 3.0 molar solution, and we had 50 milliliters of it, or 0.050 liters. So moles per liter times liters, the liters will cancel. That means that we have 0.15 moles of sodium hydroxide total. And we're not changing that number. We're not reacting it with anything, and we're not adding any more sodium hydroxide. And remember, in this problem, we want to have 0.50 molar or 0.50 moles sodium hydroxide per liter. So what we can do is use that 0.50 moles sodium hydroxide per liter and the 0.15 moles of sodium hydroxide. We'll use dimensional analysis, again, to cancel out moles of NaOH and get the new volume, which is really cool. So, but remember, the moles in the initial stuff equal the moles in the final solution, and we're not changing that number at all. So we take the moles of sodium hydroxide, the total moles, and this is nothing more than basically dividing by 0.50. Now I've listed it there as a liter per 0.50 moles, and you can totally do that. But we're doing that because the moles of NaOH are going to cancel out, and you're going to be left with just liters. So 0.15 divided by 0.5, 0.30 liters is going to be the volume of the final solution. And if you multiply that by 1,000, that means you'd have 300 milliliters in the final solution. Now, there's one more little thing we have to do. 300 milliliters represents the volume of the final solution, but we started with 50 milliliters of volume. All right, that was this number up here. So what this means, we'd want to add 250 milliliters of water to 50 milliliters of 3.0 molar sodium hydroxide to make 300 milliliters of 0.50 molar sodium hydroxide. You don't want to add 300 milliliters when 50 milliliters is already there. You want a total volume of 300 milliliters. So we would go 300 minus 50 or 250 milliliters of water to make our solution correct. Pretty cool. Scientists will often use this expression to calculate the new diluted concentration in a much easier way. And instead of calling it M initial, V initial equals M final times V final, sometimes people will abbreviate it something like MIVI equals MFVF. I means initial and F means final. Or sometimes it's C1V1 equals C2V2, where C is the concentration. But all this is really saying, remember, molarity is moles per liter. And if volume is in liters, then it's saying moles initial equal moles final. All right? They just like cancel out. So again, molarity initial would be moles initial divided by volume times the volume. Volume cancels. On the other hand, the other side, you've got moles final divided by volume final times volume final, and they cancel out. Final moles equals initial moles, which is what we said earlier. So this whole M1V1 equals M2V2 or MIVI equals MFVF, it's just saying the moles are equal. But the reason why scientists like that, and the reason why I'm pointing it out here, is because you can use volume in milliliters if you want to, all right? They will cancel each other out. You are still welcome to go through and make them all liters, but if you want to use milliliters here, it's quite all right. So molarity, big M, has to be 60 moles per liter. But volume, as long as they're both the same kind of volume, you can use milliliters or liters or whatever you want. You'll see examples of this later on in your problem set. But again, if in doubt, turn everything into liters, you'll be good to go. Here's a question. You add 60 milliliters of 0.25 molar HCl to a 500 milliliter volumetric flask. Then you add enough water to make it up to the mark of the flask, which means you have a total volume of 500 milliliters, by the way. What's the concentration of HCl in the diluted solution? And conveniently down here, I left up the equation where we need to use M1V1 equals M2V2 or MIVI equals MFEF, whichever one you want. So 60 milliliters is VI, the initial volume. 0.25 molar is the initial concentration, MI or C1, whatever you want to call it. And if you're filling it up to the total volume, then VF or V2, whatever, would be 500 milliliters. And we want to solve here basically for MF, the final concentration, or C2, whatever you want to call it. You're welcome to keep those numbers as milliliters if you'd like to. You could also change them over if you'd want to liters. It's not going to make any difference. Volumetric flasks are very accurate. So if it is a 500 milliliter volumetric flask, I would call the sig figs on that like 500.0 or 500.00. They're very, very accurate if you pay attention to the little mark on the flask. So there's not a dot by the 500, but that doesn't mean that's a 1 sig fig number. Anytime you fill it up a volumetric flask, that's one of the higher precision kind of things in the glassware. So anyway, don't worry about sig figs for 500. 0.25 moles per liter, 2 sig figs, that's going to dominate your sig figs in this problem. So again, what you want to do is you want to have the initial volume times the initial concentration, and that's going to equal final concentration times final volume. But we're just going to solve for the final concentration, so divide by the final value. There I put in a 500 dot, kind of cheesy, I guess. But anyway, you get the idea. That's going to be 2 sig figs because of the 0.25. 60 times 0.25 divided by 500, 0.030 moles per liter, answer C. But you could also use 0.0600 liters times 0.25 divided by 0.500 liters, same answer. So if you use M1V1 equals M2V2, you can often get away with using just milliliters and milliliters instead of liters and liters. Again, nothing wrong with using liters and liters, but why not?